Okay, so we want to find the roots of this equation. Basically, that means we want to find where it equals 0. And the first thing we always try to do when presented with a polynomial equation, with the polynomial equation, is we try to factor the thing. We see 4 terms here, so we attempt to group it, and I can tell you it's not going to group. Oh, how sad. So when it doesn't group, we turn to our rational root theorem. And our rational root theorem is kind of cool. It says that if this thing has a rational solution, it comes in the form p over q, where p is a factor of this last constant term, and q is a factor of this leading coefficient. So the factors of my constant term are 1 and 2, and the factors of the leading coefficient are 1 and 3. So my possible rational roots are, if I chose a 1 as a denominator, it's like any combination of these. So if I chose a 1 as a denominator, I could have 1 over 1 or 2 over 1, so 1 or 2. And if I chose the 3 as the denominator, I have 1/3 and 2/3. And I could have plus or minus of any of these. And that narrows down the possibilities for rational roots from an infinite possibility to just those 8. And if none of those 8 works, then this has no rational roots. Could have some imaginary roots, could have some irrational roots, but these problems are rigged. Something's going to work for us, so we're going to be okay. So what we're going to do now is we're going to start testing these. You can test them just by simply plugging in a 1 and seeing if that gives you 0, plugging in a 2, seeing if that gives you 0. But we're going to test it using synthetic division, because not only will that test it, it'll help us later on to whittle the problem down a bit. So, synthetic division, I'm going to write my coefficients here, making sure I don't need any placeholders. I've got 3, 2, 1, none for my powers, so they all go down. No placeholders needed. So 3, 4, 7, 2. And I'm going to start by trying to a 1. So I'm going to drop the 3 down and do my synthetic division. So this is 1 times 3 is 3, add 7. 1 times 7 is 7, add 14. 1 times 14 is 14, add 16. If this were a root, then this would have been 0 by our, there's a factor theorem. So because this doesn't equal 0, 1 is not a root, we try again. So maybe I'll try usually I try 1 and then -1 and then 2 and then -2 and then 1/3 and then -1/3 and so on. I'm going to skip here to -2 just because I think it'll show you a little bit more what the synthetic division is like. So I'm going to drop the 3 down first. You always start by dropping that first number down. And then you multiply. So -6 and add -2. Multiply 4, add 11. Multiply -22, add -20. Bummer, still not equal 0. Blech. So you keep testing. And don't worry, these problems are rigged. One of them should work. And I'll take you to them right now. We're going to try that -1/3. So again, with my coefficients 3, 4, 7, 2, drop the 3 to start, and you multiply, -1, add 3. Multiply, -1, add 6. Multiply, -2, add 0. Yay, we did it. We found one. So now, not only did we find one of the roots of this, we have successfully whittled this equation down. We divided out the factor x plus 1/3. We divided this thing by x plus 1/3 and got this left. We got 3x squared plus 3x plus 6. And we're looking at that and we're like, oh, that's a quadratic. I can solve this no matter what. So even if this thing doesn't factor, I can use quadratic formula. I can see I can divide them all by 3, so I'm going to pull out a 3 first. And I'm going to attempt to factor, and of course it doesn't factor. So that's okay. Like I said, I can use quadratic formula. So I have negative b plus or minus square root, blah, blah, blah. So it's going to be negative 1 plus or minus the square root of 1 minus 4 times 1 times 2 all over 2 times 1. So negative 1 plus or minus the square root of negative 7 over 2. So negative 1 plus or minus I root 7 over 2. Negative underneath that radical, pop that I out. So my final roots for this equation are negative 1/3, negative 1 plus I root 7 over 2, and negative 1 minus I root 7 over 2. Notice there were 3 solutions for my third degree polynomial, and that is all.